Chem 213. Jason's changed a little since Friday, a little shorter maybe, higher pitched voice. So Jason's away this week, so I'm going to be teaching today and Wednesday, and we're going to be just covering now reactions with benzene rings primarily. So a couple reminders, no office hours today because Jason is not here, but we will have TA run office hours on Thursday from 11:30 to 1, so that will be me and Sarah running those. Come with your questions. Try to stump us. Actually, don't do that. And then Canvas Quiz 5 is open, and it's due at 5 on Friday. Pretty typical. Midterm 2 is coming up March 24th in the evening. If you are with the CFA, make your booking. Problem sets should be coming out soon, as well as practice midterms. And then still some time to design a question and post it on Piazza. And please include your answer if you are posting it on Piazza, so they can be used as good study tools. So last class, it was covering phenol and phenoxide reactivity. So you covered oxidation of various benzene rings and the Colby carboxylation. And today's class, we're going to be covering more. But before we do that, a review question. So I'll give you guys some time to do this review question. All right, for the first one, does anyone know what these conditions are? We use the short form a lot on tests. Jones, yeah, these are Jones. And what is the product? Carboxylic acid. Does anyone know the name of the carboxylic acid? Nice, solid. Okay, and for the bottom one, what is the functional group called? Louder. This is a phenol, yeah. And then what is the product? What's that called? An ether, yeah. Nice and easy. I guess I'll give you guys less time to do the other ones. All right. So this class, we're going to be covering a very important reaction, nitration. This is how you make TNT. That's what I learned in second year, so I'm passing it on. Then sulfonation and halogenation of benzene and other aromatic rings. So when these arenes undergo reactions, they do so in a way that at first disrupts the aromaticity, but then later it will reform the aromaticity, which is why these reactions can happen. So electrophilic aromatic substitution is where this aromatic ring acts as a nucleophile because it does have these double bonds that supposedly have electrons that can go off and act as nucleophiles. They're not like your typical nucleophile just because they are aromatic, but they can undergo these reactions. And the general form, the general reaction form is some aromatic plus an electrophile gives the aromatic plus the electrophile and the hydrogen, which is abstracted, that reforms aromaticity. And so the general mechanism for this is this lone pair acts as a nucleophile, and it comes out and grabs the electrophile. And this complex is called a sigma complex because it has a positive charge. And then we have some base around in the system, and it will come and abstract this hydrogen and regain aromaticity. So the nice form of this is this. And the reason why this is relatively stable is that this positive cation can undergo resonance stabilization. So there's a couple forms of this cation that are stable. Yep. Yep. Yeah, if I'm going too fast, please slow me down. So between these two steps, step 1 and step 2, which do we think is the slow step of the reaction? Step 1. Step 1 is a slow step. Why? Yeah, it's breaking aromaticity. And then step 2 is fast. Why? Acid base, yeah, and it's reforming aromaticity. So this is super favorable. All right, so yeah, step 1, slow step. It attacks the electrophile, forms a resonance stabilized intermediate, and then the next step is where it is fast abstraction of the hydrogen, so acid-base chemistry to restore the aromaticity. So this sort of electrophile grabbing from the aromatic system and then regaining aromaticity is pretty much exactly what we're going to see over and over again in this lecture. So you'll probably all be saying, and then it regains aromaticity in your sleep at the end of the day. So we're going to do nitration, sulfonation, and halogenation, and then next class we're going to be doing the Friedel-Crafts alkylation and acylation. And those are some really interesting reactions that are pretty useful. So the nitration of a benzene ring introduce, shockingly, a nitro group, and the electrophile for this is the nitronium ion, which looks super nasty, and that's because it is super nasty. And you make this nitronium ion through the dehydration of nitric acid using concentrated sulfuric acid. So if you're going into the lab and you're trying to find these reagents, you're going to have to go in the strong acids cabinet, which is like really crusty and like nobody's really opened this in a while. And because everything is super crusty, you just open it, you just smell this pungent smell of acid. And the bottles are all crusty. And so you're going to mix these two together through the dehydration mechanism, whereby these electrons go up and grab a hydrogen, and then it goes and makes deprotonated sulfate, something like that. Anyways, pretty stabilized, resonance stabilized. So then we form and then this lone pair on the oxygen can go down. Oh, this is protonated. And then this kicks off water. So then we form our nitronium ion and water. And this is it again shown with nicer arrows. And And so the mechanism is just like the generic mechanism where the pi electrons go in, attack the nitro group, forming, what's that intermediate complex called? Yeah, the sigma complex. And then the next step is we'll just use the water because it's around. And it's a decent base in this system. It'll go in and abstract this hydrogen to regain aromaticity. So here is, again, the nice looking mechanism. And so the slide shows that under normal conditions, one nitro group is enough. That's sort of what the ring wants to take because the nitro group is super electron withdrawing. So all of a sudden, once you put this nitro group on, you're sort of taking all the electron density towards it, and it's pretty deactivated. The only thing is, if you make it non-nice conditions and heat it up and heat it up and heat it up for a long time, you can make a trinitrated species, which is trinitrotoluene. And this is why it's a fun reaction, because this is TNT. And I work a lot with kids in the summer at camps, and we're making homemade stickers. And I made one for TNT, and I put it on my laptop. And I didn't think anything about it until I was going through airport security. And they're like, take out your laptop. I'm like, oh, oopsies. And I put my laptop on the tray, and the TSA agent's like, oh man, organic chemistry was my worst subject. And it's like, I can kind of tell because you couldn't identify this species. Anyways, so that's TNT, and that's how you make it. But you really do need high temperature for a long time. So, and you're using that like nitric acid and strong sulfuric acid. So if you can make this without hurting yourself, that would be incredible. All right, so this is a really important reaction, so nitration of a benzene ring, because then you can reduce it using your Raney nickel, your hydrogenation conditions. So typically that would be hydrogen gas at some pressure and a catalyst, a metal catalyst, so nickel, palladium, or platinum. And then you can make this amine species. So this together, when it's on a ring, this is aniline. That's just what it's called. And then you could also reduce this using iron and HCl. And yeah, that's another way, depending on the functional groups that are on your molecule. But I mean, given the super acidic conditions, this is not really something that you want to be doing in a later stage. If you're doing like a total synthesis, this is not a step that you kind of pull out at the end. You're like, and then I'm going to nitrate my benzene ring, because you will probably obliterate everything else on your molecule. So next we have sulfonation. So again, we're going to be doing this in a two-step fashion where we're forming our electrophile, which is called HSO3+. And then we're going to be using that as the electrophile and taking our benzene ring to be our nucleophile. So you make this by fuming H2SO4. So you again take your super concentrated acid, and then you take this SO3 species. And if you look up online fuming H2SO4, it actually is fuming. So it's like a beaker, and it has these sort of deadly looking gases flying off of it. Again, not something you really want to be making. Typically, you can buy all these feedstocks. So if you're in the lab, and if you're doing undergrad research and your grad TA or like the grad student overseeing you is like, oh, can you get me like the nitrated benzene? And you're like making it with, like, don't do that. Just go and find the bottle of chemical that already has done this, because nobody wants to file that paperwork. So again, the general mechanism is we're going to be activating this. Pretty simple. we're going to be using these lone pairs to grab a hydrogen and make this species. And then in the next step, we're going to be using that as an electrophile. Any questions so far? Pretty straightforward. All right, mechanism drawn nicer. Again, use these lone pairs or the pi electrons attacking the electrophile, form the sigma complex, and then re-aromatizing. All right, the last reaction we're going to be covering today is the halogenation of benzene. And so this time we're going to be using bromine, but with iron as our electrophile. And then we're going to end up with an aryl bromide and a lovely acid. So iron is not actually a catalyst. Again, we're going to use iron and bromine to form an even more electrophilic species. And we have to form these super highly electrophilic species just because our aromatic ring is typically inert and just doesn't really want to react. So we have to really, really pull it out there to react. So this sort of reaction mechanism, so 2 irons, 3 bromides makes this species, which in situ looks like this. And you can imagine that iron comes out, or bromine sort of associates, and we have this partial positive charge on the bromine and a partial negative charge on the iron. And so now if we use this as our electrophile, which is pretty active, we're once again going to be taking this lone pair and grabbing a bromine, and so that's just going to form that bond. Forming this sigma complex. And then using a base in the system to abstract the proton and regain aromaticity. So this is the mechanism drawn nicely. And I will then have a question for you all, and I want you to rationalize and talk amongst yourself for a little bit. If we have an indole ring, which looks like this, and we use any of the conditions talked about earlier today, so we have either nitration or sulfonation or halogenation, where on this molecule is it going to react? So I'll give you all like 2 minutes to talk. All right, so coming back, indole, is it aromatic? Yes. Why is it aromatic? Someone will put their hand up? Yes. Yep. Yep, great. It follows all of the rules for aromatics. So does anyone have an idea of where it will react on this system? All right, let's go through. Does anyone think it's going to react here? Don't all speak at once. Okay. What about this position or this position? No. Okay. What about this position? No one's saying anything. Okay. What position do you want it to react at? That one? Okay.
And it would have the least inductive pulling of electrons away, so it'd be the most nucleophilic.
Okay. Okay, nucleophilic on the aromatic system. So this is a bit of a mean question because it's actually a bit of a throwback to lecture 25. But does anyone see like a functional group embedded within indole that you learned? Does anyone see, what is this structure called? It's an enamine. So this position, I was kind of sad when no one picked this, but this position is actually what's going to get nitrated or sulfonated or halogenated because you can form this where the electrons kick down in an enamine fashion and pick up an electrophile. And then you'll have some base around, and it will re-abstract it. Anyways, that's my extra little question for y'all. So it's not always what you might think, but it's always good to evaluate the whole molecule and find the functional groups. Yes?
So by that reasoning of like the electron from the nitrogen pushing in, can you also do that for like the other spots where you have like that resonance and it kind of picks up an electron?
Yep. Yeah, there's definitely some reactions that I've worked with where you can actually go through and depending on the reaction conditions, and it will also depend probably on the electrophile, you can selectively get it at one of these other positions, but it requires a little bit of picking around with the reaction conditions. Yeah, but typically this C3 position is what it's called on the indole is the most electrophilic, nucleophilic. Yeah. Any other questions? All right, so that's actually the whole lecture for today. Yeah, I could start on Wednesday's lecture, or you guys can all go early. All right, I'm seeing some thumbs up for going early. So thanks for coming. Thanks for your attention. See you on Wednesday.